Welcome everybody to the next Heidelberg Astronomical Colloquium. This week we're doing our single colloquium on planetary science this semester, and we're very glad to welcome Bertram Bitsch from the Max-Planck-Institut for Astronomy, who will talk today about some topics about how to build planets with reference to JWST data. So we're very much looking forward to that. Bertram did his PhD in Tübingen University, working under the supervision of Professor Wilhelm Clay. And already then you started the journey, which is going to lead you to the JWST. Following that, Bertram went to the Lund Observatory in Sweden as a senior research fellow. Oh, no, actually, just before that, you were a postdoctoral research assistant at the Côte d'Azur, South France. And then you moved up to the north of Europe. But at Lund Observatory, Bertram was awarded a prestigious ERC starting grant, which to do work at Heidelberg, he came here in 2018, started the group, an independent research group, looking at the planetary science. This thing is called, what's it called? Your research, the Pandora Project, yes. Today we'll probably hear, I think, the sort of more mature results from that. We're particularly interested because this is our last chance for a while to hear Bertram, because he's been awarded a faculty position at Cork University in Ireland. So Bertram, thank you very much, and tell us about how we can make planets out of dust, please.
Yes, thank you very much. Can you hear me? Sound is okay? Perfect. Okay, thank you very much. Thank you for the invitation. It's a great pleasure for me to talk to you a bit about the planet formation theory in the James Webb era. So I would like with a plot that is actually a few years old, but essentially, basically, if you look at the plot, an updated plot in these days, you would just see that we detected, of course, many more planets. But what I like about this plot is still that it shows you the different detection techniques. So what you have is orbital distance against planetary masses, and the different colors gives you the different detection methods that we use in order to find planets. In black, of course, we have our planets of our own solar system. You already noticed that Mars and Mercury are missing because these planets are actually just too small for the Y scale that we have on this plot, which already illustrates that it is very hard and very difficult to detect these small planets around other stars. If you look in this plot, you maybe detect three different groups of planets. Down here, you would have the group of super Earth sub-Neptune planets, so planets a few times the mass of our own Earth. And there's two other groups that I will actually mainly focus on. These are the so-called cold Jupiters and hot Jupiters. So these planets are similar to mass in our own Jupiter, but they of course orbit at slightly different distances. So the hot Jupiters, as you can see here encircled in black, these are planets that orbit very close to the central star, where it is very hot. Actually, so these planets can actually have equilibrium temperatures above 1000, 2000 Kelvin. And this actually poses a question that we actually have to ask, because if these regions of the inner disk are actually really that hot, then it might actually be too hot to form planets directly in that region, because at these temperatures, the building blocks of planets, so the small dust particles, they might actually all evaporate. So we actually have to ask the question, where did actually these giant planets form in these protoplanetary disks, and how did they actually get there where we observe them today? So the question that I would like to address a little bit in my talk is the question, where did these giant planets come from? So again, this is the same plot. There's two main pathways to make these hot Jupiters. You could first make a cold Jupiter in the outer regions of the disk. You could then have scattering events that bring this planet to the inner regions of the disk, or maybe it's more like a smooth migration during the gas phase of the protoplanetary disk. And the question is, how could we potentially distinguish between these formation channels? So one idea that was put forward actually a bit more than a decade now by Öberg et al. Is the idea that we could actually distinguish these formation pathways by the atmospheric composition of these planets. So what you see here in this plot is the C over O, so the carbon over oxygen ratio in the protoplanetary disk as a function of radius. You see here two different curves. So the solid line represents the solids, so the dust or planetesimals that will later make on the planet, and the dashed line represents the gas carbon over oxygen ratio. And what's happening here is the following. In the outer regions of the protoplanetary disk, it is very, very cold and everything is frozen. So the protoplanetary disk, so the solids in this disk, have a C over O ratio that would correspond to the stellar value because everything is frozen. Then as we move closer in, the disk becomes hotter, and in this case, CO starts to evaporate. This, of course, implies directly that the gas C over O ratio should be 1 because, you know, CO has a C over O ratio of 1. Then as we go further in, then we have different other molecules that can evaporate, and we have different jumps in this diagram. And the idea here is now, if you have a planet, and we can observe the atmospheric composition of this planet, maybe we can directly basically read off from this plot where this planet could have formed. But of course, is it really that simple? That's of course the question we can ask. It's quite obvious. I have 30 slides left, so the answer is no. Okay. So how do we do this? So how do we form planets? So we know that planets form in a protoplanetary disk. So you see here a micrometer observations of sphere of the TW Hydra disk, where you see you have different rings in the micrometer distribution, but we can also, so this is the micrometer dust. We can also look at the millimeter grains. I will call these millimeter grains pebbles. I'll explain later to you what this actually means. So this is in this case just larger particles. You first of all see that there's a certain size difference in this for the different dust sizes. So this is the same disk, right? And now within this disk, we actually have to somehow form planets. We have to arrive to this kind of distribution. And this is a very challenging journey because we go from micrometer sized dust grains, so 10 to the minus 6 meters, all the way to planets 10 to the 7 meters. So over 13 orders of magnitude in size. And the question that we have to answer is like, how do we actually model this growth of the planets? Because it's very clear we cannot model every single grain. So how do we do this? So we normally work in this paradigm, which is the core accretion scenario, where the idea is we first build a planetary core that can then accrete gas onto it. So we start with a star that has a protoplanetary disk around it. And in the small disk, you have our dust grains, micrometer dust grains that can grow to these millimeter, centimeter sized pebbles by coagulation, condensation. These pebbles can then form planetesimals. Think of something like asteroids, like 10 to 100 kilometers in size. Then these pebbles and planetesimals can accrete together to form terrestrial planets, or we can even make gas giants if you reach core masses that are large enough. At the same time, we have to care about the gravitational interactions between these planets and the protoplanetary gas disk itself that you can see here that leads to planetary migration. So you see the from a simulation, you see here the planet, it exerts the spiral waves in the disk that allow an exchange of angular momentum between planet and disk. So the planet actually moves through the protoplanetary disk. Once the planet becomes much larger, it can open actually these very deep gaps in the protoplanetary disk and migrate on a slower speed to the so-called type 2 migration. At the same time, we have to care about the disk evolution, and then we put this all together in our simulations in order to see can we actually match this population of planets. We have to care about our super Earths, we have to care about our giant planets, and we have to care about the composition. So what are these planets actually made of? And this, of course, is very, very complicated process, and you can lose many hair over these different questions. And basically each of these arrows, and I probably forgot many arrows, is actually an independent research field of its own, where a lot of different efforts go by many different groups to explore all these different processes that are involved here. Even though there's still a lot of open questions, the general framework that this process works, that how we can grow from dust, from micrometer-sized dust all to the planets, I think is still is actually paved out. The roadmap is there, which we have to think about more the detailed processes that are involved in here. So in this talk, I would like to talk a little bit about 4 different topics. So first, I would like to explain to you how we can actually model the formation of these planets. And then I would like to talk about what are the conditions to make giant planets. I will talk about how does pebble drift influence the composition of the protoplanetary disk. So how these small millimeter, centimeter sized objects influence the composition that we can observe. And then, of course, the question that I posed in the very beginning, can we actually constrain the formation location of the planet via the atmospheric observations of these planets? So let's go directly into the model for the planet. So what tools do we need for this? So the first thing we have to actually care about is the growth of the grains. So if we look, we have these small micrometer-sized grains, and we have to grow them to larger grains. You see here in this cartoon, there's two columns on the left, on the right. Where on the left column, this basically implies there's two particles that would interact that have the same size, and on the right is two particles that have different sizes. And you see that there's different outcomes for these collisions. What can happen? So you could have a hit and stick, where these particles just come together and stick and could eventually grow. And of course, more violent, there's also fragmentation. So if the particles actually collide and then would fragment. And this, the outcomes of these collisions, they are mostly dependent on the velocity between these particles collide. So basically, the speed determines the collisional outcome. It's like, you know, if you park your car in the garage and you go very slow, maybe you just do a small bump, but if you go way too fast, you know, you fragment your car, right? So basically, it's very similar in these protoplanetary disks. So there's a speed between the particles determine the collisional outcomes. Additionally, I should say that larger particles normally have larger velocities. So basically, if you become bigger, you become faster. I'll explain this in the next couple of slides. And this actually then prevents the growth by this process above centimeter to decimeter sized particles, depending a bit on the parameters that you would use. So basically, what it implies is we cannot just grow from micrometer sized dust all the way to planets in one go. We have to have some processes in the middle. Now, these particles, they also move through the protoplanetary disk. And the reason for that is because in this protoplanetary disk, so we have the disk around the star, and then we have a gradient of pressure in this disk, which is caused by a gradient of temperature. So the inner disk is hot, and the outer disk is very cold. And of course, the inner disk is also much denser than the outer disk. So we have a radial pressure gradient in this protoplanetary disk. And the gas in itself is actually supported by the gas pressure. You see the equation here. And so the gas actually orbits on a velocity that is slightly sub-Keplerian. The small dust particles, on the other hand, they do not feel this pressure gradient, and they would like to orbit on a Keplerian velocity. So you have a velocity difference between these between the gas and the particles, and that actually robs angular momentum from these particles and allows them to drift them inwards. And this inward drift can actually be very, very fast. It can be much, much shorter than the lifetime of this protoplanetary disk. So you can do the calculation and see if you have like a centimeter, decimeter sized particle in the outer disk, it would actually go into the inner disk on timescales that are 2-3 orders of magnitude shorter than the lifetime of the protoplanetary disk. So the dust is washed normally inwards. So the question is, how come that we then still observe these protoplanetary disks? Well, one idea is actually that there are so-called pressure bumps in these protoplanetary disks. So you see this here in this cartoon. So this is the pressure gradient of the protoplanetary disk, and you see there's a maximum, a local maximum of this pressure gradient in this disk. And this actually allows us to accumulate the particles because the particles want to go to the point of highest pressure. And with this, you can trap particles in this disk, and then if you actually trap them at a pressure maximum, they will not necessarily move towards the inner of the disk. So if we can actually use this and look here, for example, this is HL Tau, one of the first protoplanetary disks that were actually observed with ALMA. And you'll see gaps and rings in this protoplanetary disks, and basically this basically is an indication that we have in these bright rings, we have a larger accumulation of particles compared to the gaps. And in order to do so, we need pressure bumps in these protoplanetary disks. There's many, many different ideas what can cause these pressure bumps in protoplanetary disks, but essentially we need something to stop the inward motion of the particles, and that would be the pressure bumps. Now, these small millimeter grains, when they actually drift through the disk, we can actually make use of them and accrete them onto our planet in some process that is called a pebble accretion. The idea here is we have our protoplanet here, and then this dashed line would correspond to the Hill sphere of this protoplanet, so where the gravity of the planet dominates over the gravity of the star. Now these small millimeter-sized pebbles, they actually move towards the planet because of the effect of the gas drag that makes them actually drift through the whole disk. So your planet sits there and the pebble comes to you. Now these pebbles, if they're in the good size, they can actually just spiral down towards the planet because they lose the angular momentum due to the friction of the gas. So the pebbles can be accreted very efficiently. The accretion rate of pebble accretion depends on a few parameters. So it depends on this Stokes number, which is basically just a measurement of the size of the particle, on the Hill radius, so the mass of the planet, Keplerian velocity, and the surface density of the pebble. So how many pebbles do we actually have available? I should note that there's a few caveats to this. So for pebble accretion would only become efficiently once we actually have embryos of the mass of the moon. If our protoplanet is much smaller than that, then also pebble accretion is not very, very efficient. So you might actually need some initial collisions from these 100 kilometer sized planetesimals before pebble accretion can actually take over. But additionally, the moment you reach this mass, your planet can actually grow very, very efficiently. The reason for that is because the planet has access to the full mass reservoir of the protoplanetary disk. Because your planet sits there, and basically all the pebbles from the outer disk actually would pass your planet. So you have access to a large reservoir mass, even though the planet would, of course, not accrete all the mass that passes it. So it's just like a few % of the mass that would actually pass the planet that would be accreted. Now, of course, a pebble accretion at some point would also stop, so we cannot grow all the way to infinity, which of course is also very good. And what happens and why that happens is because the planet starts to open a small gap in the protoplanetary disk. You see this here in this simulation that gives you the density perturbation. So one would be the unperturbed disk. You see we have our planet here, and you see the planet has opened a small gap in the protoplanetary disk. The reason why this planet opened the gap on the disk is the exchange of angular momentum between the planet and the disk. So the inner disk normally would like to give angular momentum to the planet, but if the inner disk gives angular momentum away, you move inwards. At the same time, the planet gives angular momentum to the outer disk, so you push the outer disk outward. So the planet slowly pushes away the material from its orbit. Now, if the outer disk actually gains angular momentum, it also increases the velocities. So you see this here in this plot here, where we plot the azimuthal gas velocities in the protoplanetary disk. So our planet here again sits at 1, and here in the outer regions of the disk, where far away from the influence of the planet, the disk is sub-Keplerian. So our small pebbles would actually slowly drift inwards. Now, close to the planet, if the planet becomes big enough, we have actually accelerated the gas to these super Keplerian values, and our pebble drift would stop. So basically, if you want, you can compare this like here. You're actually for example, if you go with a bicycle, you go against the wind, and here would have the support of the wind, so you can actually you would actually stop here. Now, this pebble isolation mass, so the mass at which the planet can open this gap and generate a pressure bump exterior to its orbit, depends very, very crucially on the disk properties, as well as on the particle size, but also on the stellar mass. So normally this pebble isolation mass is smaller for smaller stars. Now, again, to illustrate this, so this is just a cartoon that shows you what happens. So we have our massive planet here that would open up a gap, and you would basically generate this pressure trap, and you can trap these particles in this pressure trap next to the planet. And now, of course, we can actually link this to observations of protoplanetary disk. And the idea is could be that basically these gaps in these protoplanetary disk, these gaps and rings are caused by planets. Of course, this does not imply that every gap has a planet. It just means planets are one way to explain these structures that we see. Okay, so basically, once the planet has reached this so-called pebble isolation mass, the planet would actually stop accreting pebbles, would stop accreting solids, and the planet can slowly start to contract its planetary atmosphere. You see this here is an old idea. This is basically what the core accretion scenario is about. So you accrete gas onto the planetary core. So after the core is formed, we can accrete our envelope. So this would be the dotted line in this plot. And then at some point, we actually transition into the so-called runaway gas accretion phase when the mass of the atmosphere is similar to the mass of the planetary core. This contraction phase here is of course studied very, very intensively, and it depends very strongly on the mass of the protoplanetary core, or also on the opacity in the in the envelope, because the planet actually here wants to cool, and that depends on the opacity in the envelope. Another idea is, of course, as your planet grows and you still bombard planetesimals into this atmosphere, they would release heat, and if you heat up the atmosphere, well, it's very difficult to cool and to contract. Additionally to that, so this is just a 1D picture. Additionally to that, this gas accretion process is actually a 3-dimensional process where you have flows that come from the upper levels of the gap into the planet and give all sorts of very, very interesting hydrodynamical patterns. So to really understand this gas accretion processes, you need 3D simulations that also resolve the thermodynamics of the protoplanetary disk. And this is, of course, very, very hard and very expensive to do, but we have to do this in order to really understand this process. Now, with all these tools at hand, we put this all into a model, and now we ask, what are the conditions that we need to actually form giant planets? So for this, we have a code, the ChemCom code that we published a few years ago. It's a code that includes many different physical points. So we have a viscous disk evolution. We have our pebble growth and drift model. So the particles grow and then they drift through the disk. These pebbles can evaporate and recondense at ice lines. We do not take care of the chemical evolution, but I will explain this to you in a bit later. We have the accretion of pebbles onto our planetary cores. We have gas accretion, and our planets migrate through the disk through the gravitational interactions. And you see here, this is the flow chart. What happens? So we start with a protoplanetary disk where we put our input parameters, mass, radius, metallicity, and so on. Then we can calculate our disk size, and then as the planet grows, it migrates through the disk and gives the feedback onto the protoplanetary disk that then influences the evolution of the, for example, the pebble density in the protoplanetary disk. So as the planet grows, as I said, it can open a gap, and then with that you can stop the evolution of the pebbles. Now, with this, we can start to look how do planets actually grow and migrate in the protoplanetary disk. So these are the so-called growth tracks, where the idea is that we plot the evolution of a planet in a function of semi-major axis versus planetary mass. So the planets always start down here, and then they start growing. So the solid line corresponds to solid accretion. So we accrete the pebbles, and then the dotted line would correspond to the gas accretion phase after we have reached the pebble isolation mass. These triangles here would correspond to a transition from type 1 to type 2 migration. So where we go from a normally fast migration to a slower migration. And these circles correspond to time steps. So each circle corresponds to 500,000 years. So you have here an evolution of 3 million years in total. So this is a protoplanetary disk where these planets grow. So it's actually only one planet per time. So this is actually 4 different simulations where we just put the planet at different positions. For the disk, in this case, we have a disk that is 10% the mass of our sun. It's a rather large disk with a radius of 200 astronomical units, and we have a nominal dust to gas ratio of like 1.5%. What you see here in these simulations is that in the outer disk, our planets actually grow rather quickly. You reach pebble isolation mass, you accrete gas, and you become a gas giant in the very end. The guy in the inner region of the disk, it also grows rather quickly. We reach pebble isolation mass, but then this planet actually stays rather smallish because this pebble isolation mass is very small. So it takes very, very long for the core to actually accrete gas. And then we later on become like a sub-Neptune in the inner regions of the protoplanetary disk. Now, this simulation looks like, okay, it seems very, very easy enough to grow giant planets. You see here, these guys, they all have masses of between 100 and 1,000 Earth masses. So we make very successfully our giant planets. Now, we can actually change a little bit the parameter space that we investigate here. So this is again our standard simulation. We can now compare this to a disk that only has 1% the mass of the sun. So it's like 10 times less material available to grow planets. And you see there's a very dramatic effect here, where the planets actually do not really grow too much. And this is caused by the fact that this smaller protoplanetary disk has, of course, less material available to build the planet. So you just have not enough material in this scenario to build giant planets. We can additionally also vary the starting time of these planets. So here in this plot here, we put our planetary embryo in after 100,000 years. So the planet starts to grow very, very early. Here, on the other hand, we implant the planetary embryo after 900,000 years. So the disk already evolved for nearly 1 million years. And this means a lot of the pebbles actually have drifted towards the inner disk and are lost, and the planet cannot accrete them anymore. And you see this here, I think very, very dramatically, that the planets here, they basically kind of starve and just migrate a little bit through the protoplanetary disk. You see the difference is very, very striking. Now we can, of course, compare, now also make a simulation where we increase the total dust to gas ratio. So in this case, it means we have more solids, more pebbles available to build our planets. And you see there's actually not too much of a difference between these plots, because here we already had enough material available to planets. And if you have even more material available to build planets, well, you still make giant planets, right? Now we can also take a little bit a closer look at if the dust to gas ratio actually has an influence if we change the overall disk mass. So here we have again these two panels with the different growth tracks, where we have here on the left a disk mass with 4% the mass of the sun, and here with 7% the mass of the sun. The green lines correspond to our standard simulations with 1.5% metallicity, and the purple lines correspond to the 3% metallicity. And you see, for example, here in this disk with 4% the mass of the sun for this planet starting here at 10 AU, you see in the disk with the lower metallicity, you maybe just make a small sub-Neptune-ish kind of planet. But if you had a higher metallicity, you would actually make a giant planet, because your planet can grow more efficiently. The same is true for the more massive disk for the very outermost planet. So if you have a higher metallicity, you can actually grow to a larger planet. So we can conclude from this that a higher dust to gas ratio can compensate somewhat for an overall lower disk mass. This, of course, is not very surprising, because we can actually see this in observations where the occurrence rate of giant planets is actually much larger for stars with an elevated metallicity. So this is, of course, in agreement with observations. We can now also take a look what the metallicity actually, an increased metallicity actually help us if our planets start to form later in the lifetime of the protoplanetary disk. So in these two plots, you have the starting time at 500,000 years, and here after 900,000 years. So again, the green line is the low metallicity, and the purple line would correspond to the high metallicity. And what you see in these two plots, that these lines are actually very, very similar. And this indicates that the higher metallicity cannot basically not compensate for the late starting time if you want to make giant planets. And the reason for that is, even if you have a higher metallicity, it does not prevent you to flush your particles into the inner disk very, very early, because the pebble drift is, of course, still operating also at a higher metallicity. So the higher dust to gas ratio can probably not compensate for a late starting time, for the late accretion time. And this actually implies that probably if you want to make giant planets, you have to start to make them early during the lifetime of the protoplanetary disk. Now, these are just some examples, so we can actually do the very hard work that my PhD student, Sofia Savido, actually did. So she ran like 80,000-ish simulations with different parameters. You see basically the final result of one of these sets of simulations here. So we have different sets of parameters for the disk masses, starting time, disk radius, the fragmentation velocity of the pebbles. So basically how big can the pebbles grow, for the different viscosities in the disk, and for the dust to gas ratios. And we put the planets at different orbital positions. Now this plot is a bit, let's say, full. So we try to and put this into something that is maybe a bit easier to understand. And this is the cumulative distribution of our planet. So what you have here is the cumulative distribution function for the final mass of the planets that we make in these simulations. The different color coding here in this case gives you the different disk masses that we have. So 1%, 4%, 7%, and 10% the mass of the sun. And this is the results recently from all these simulations. Here, the solid lines correspond to the 1.5% dust to gas ratio, and the dashed lines would correspond to the 3% dust to gas ratio. What you see, I think, very, very immediately, if you want to make giant planets, you certainly need a large disk mass. So if you look at the 1% mass of the sun, you see here, basically you barely make any planets the size of the Earth. So you certainly need a massive disk to make giant planets. So you need the larger disk masses. The larger metallicity, of course, is also very beneficial. Now we can also do the same game and plot again this cumulative distribution function, again for the planetary mass, but this time we do it for the starting time. So when we put the planetary embryo, so when the planetary embryo starts to accrete pebbles and gas in the protoplanetary disk. And I think it's very striking that if you look at this line here, at this yellow line here, that this is the starting time after 100,000 years. And if you move to later times, after like 900,000 years, you see it becomes very, very difficult to actually make giant planets. And this is, as I said, as the pebbles drift inwards, you will reduce your pebble flux in time, and then you just don't have enough material available to make planets if you start forming them late. So to conclude, there's many multiple factors that actually allow the formation of giant planets. So it certainly seems beneficial to have a large disk mass and to have an early starting time of your planetary embryo. Reciprocally, if you have a low disk mass and you even start making your planets very late, you will not make a giant planet. So the formation of these giant planets has to start early, and we need the massive disks for this. Now, speaking of disks, we can actually look, how does this pebble drift actually influence the composition of this protoplanetary disk? So the reason for that is because of course, motivated by observations. So you see here in this plot results from several observations. So you have here C2H2 and HCN. You see here two different groups in this plot. So we have here more like larger stars, and we have here our M dwarfs. And this, what this actually indicates, is that there's maybe an increasing C/O ratio in the inner regions of these protoplanetary disks to explain the abundances of these carbon-rich molecules. So the question that we can, of course, ask is, what is actually the cause of this change in this C/O ratio in the inner regions of the protoplanetary disk for these larger stars versus the smaller stars? So again, this is, I think, related to the pebble drift in the protoplanetary disk. So this is basically a plot that shows you the velocity of the dust and the gas as a function of Stokes number, so function of size, basically of the particle. So if your gas and the solid line corresponds to the dust. So the small dust grains, they sit over there. They have a low Stokes number, so they follow the motion of the gas. The larger pebbles, they can actually drift, they decouple from the gas and they can drift inwards very fast. You see there's like a few orders of magnitude difference in velocity. So the pebbles drift inwards much faster than the gas, which I already said before. Now, we can wonder a little bit if a pebble forms in the outer region of the protoplanetary disk, where it's a certain composition, and it would then move inwards in the disk, if maybe chemical reactions on these grains could actually alter the chemical composition of these particles. So here in these simulations from Eistrup and Henning, they have pebbles that start in the outer regions of the disk, and then they have a certain composition, and then they follow the chemical composition of this pebble as the pebble drifts inward. So the different color codings correspond to different molecules. You see, of course, always these sharp drops, and this is when the pebble reaches the evaporation temperature of the corresponding species, and the different line styles correspond to different drift velocities of the pebbles. So basically, how fast does the pebble go inwards? But what we can actually see is that there's not too much of a difference in the chemical abundance as the pebble drifts inwards. So for the remainder of the talk, I will actually not include chemical evolution of these pebbles. But what I will include is the drift and evaporation of these pebbles in the protoplanetary disk. So what you see here is from a simulation. So you have the orbital distance, and then you have the time evolution in the vertical direction. So we have here, this red line is the water evaporation front. So in the outer regions of the disk is cold and water is in the form of ice. In the inner regions of the disk, water ice can evaporate and we would have water vapor. What happens here now is that we have our pebbles and they drift inwards and then they evaporate and release the vapor in the inner regions of the disk. And this can lead to a very large pileup of this water vapor in the inner regions of the disk because of the velocity difference between pebbles and gas. You see this here. So the pebbles are much, much faster than the gas. So you have a lot of pebbles that come in, they evaporate, but then they are vapor and then they follow the motions of the gas. And then they would be only transported away on a very, very long time scale. So you can actually reach a very large pileup of this water vapor in the inner regions of the protoplanetary disk. And this is, of course, not only true for water, but for all volatiles in the protoplanetary disk. So the point here is that the disk composition actually evolves in time. It is not fixed with these step functions that I showed you in the beginning, where I tried to say, like, we can actually maybe link the composition of the planet to where it formed in the disk. So this static step function picture is not true. The disk composition evolves with time and changes with time. Now we can actually take a look at this. So this is simulations from my postdoc Xingyi Ma. She's actually there in the audience, so you can ask her more details about this. So the idea what we have in this plot is, again, is a plot of semi-major axis versus time. And what you have here in color coding is the C/O ratio of the gas normalized to the stellar C/O ratio. Now, what we see here, let's first focus here, maybe on the water ice line. So as I said, the water-rich pebbles come in, they evaporate and release the water vapor into the gas phase. And then you see this is a very dark blue color, which indicates that the C/O ratio of the gas is very low because obviously water has no carbon. So you release a lot of oxygen into this inner regions of the disk. On the other hand, if you go here to the methane ice line, it goes, of course, in the other direction because the methane ice evaporates and enriches the disk a lot with carbon. And you can then enrich the disk to very large carbon values. And this happens at all these different evaporation fronts. So now this is a picture of a solar mass star. And we see, if you look at the inner regions of the disk, it seems very clear that with this we can probably explain the very low C/O ratios for the inner disks around solar type stars. But now what about smaller stars? So what you first have to wonder a little bit about is the so-called viscous timescale of the protoplanetary disk, because we have our gas in the disk and that evolves with the viscous timescale, as you see here, where nu is the viscosity. So we have here two sets of simulations. And that so the solid line would correspond to a low viscosity of alpha 10 to the minus 4, and the dashed line a higher viscosity, so 10 to the minus 3. These blue dots would correspond to the positions of the water ice line in these protoplanetary disks. So first, in dark, this is our M dwarf is 0.1 solar mass stars. We see our ice lines is around 0.3 AU, and for our solar mass star, our ice lines is around 1.5 astronomical units. The reason why the ice line is closer for the M dwarfs is because the star is, of course, smaller, colder, and everything is a bit pushed further in. So the disk is colder, and therefore the water ice line is closer in to the star. Now, why is this important? This is very important for the viscous timescale, because basically the viscous timescale tells us how much time does the gas need from a certain position to actually reach towards the star. And this means for the M dwarf, the gas that would evaporate actually needs a shorter time to reach the inner regions of the disk. Now, this is, of course, not only true for water, but also for the different other ice lines. So if you look, for example, here at the methane ice line, you see for the M dwarf, maybe it takes like 3-4 million years for the methane gas to reach the inner regions of the disk. But for the solar type star, it would take more like 10 million years before that actually happens. And this is actually what you saw here in this plot, because you see the inner disk is still very, very blue in color. So the carbon-rich methane gas did not really make it into the inner disk for this in this case. And if you have a larger viscosity, basically you scale everything down to shorter timescales because the viscosity is larger. Now, the point that I wanted to make is that the carbon-rich gas has basically less travel time to the inner disk for M dwarfs, and this will actually change the composition of these disks. You see this here in this plot. So here on the right, we have our solar mass star that we looked at just now. This is a 0.7 solar mass, 0.5, 0.3, 0.1 solar mass star. What you see, I think, very clearly is that even after just like 2 million years, we already see that we can have a C/O ratio that would be larger than the stellar ratio. The black line actually indicates that we actually have a C/O ratio that is actually larger than 1 in the inner regions of the protoplanetary disk. And you very clearly see that this is an effect on that the scales somehow with the stellar mass, and the stellar mass is of course important because it gives the stellar luminosity. So it basically sets the temperature of the disk. So these disks are much hotter, so the ice lines are further away. You see this here. The water ice line here, as I said, around 1.5 AU. For the M dwarf, it's more like a 0.38. Now, of course, this is only for the low viscosity. So we have an alpha of 10 to the minus 4 here. If you have a higher viscosity, then everything is accelerated. So the higher viscosity allows a faster transport of the gas. So at alpha 10 to the minus 3, we also see that even for the solar type star, we might actually have a large C/O ratios in the gas phase after a few million years. For our small M dwarfs, basically this larger viscosity doesn't really change the picture. So that basically we again reach the large C/O ratios in the protoplanetary disk. So at larger viscosity, basically the process is accelerated. So the carbon-rich materials moves earlier into the inner disk if you have a large viscosity. This actually implies that if a lot of these disks around solar type stars would have a low C/O ratio, and the M dwarfs would have a high C/O ratio, it might actually argue for a low viscosity in protoplanetary disks rather than a large viscosity. So the point here is that I think this pebble drifting scenario actually has the potential to explain these carbon-rich inner disk regions. Now, moving on to the last idea, can we constrain the formation location of the atmospheric planets via atmospheric abundances? So the idea here is that we can actually observe the atmospheric composition of planets, and we try to link this to their formation location. You see here in this plot the atmospheric abundances of planets divided by the solar value. In this case, we have different elements: carbon, oxygen, nitrogen, and also the C/O ratio. We have here. So this is from 2 observations. So from 2 hot Jupiter planets. So we have Tau Bertus B, which is a planet that is supersolar in carbon and oxygen. And we have here WASP 77AB, which is subsolar in carbon and oxygen. But you see already they have actually a very similar, if you follow this, the big line, which is the mean value, they have very similar C/O ratios. So the question that we can ask here is, where in the disk did these planets with the different composition actually form? Now, for this, we do, again, our simulations where planets can grow in the disk. So again, this is the growth tracks of these planets. So again, the solid line corresponds to our solid phase of pebble accretion, and the dotted line corresponds to the gas accretion phase. Now, you see the planet actually, as it grows, it moves, it migrates through the protoplanetary disk. And as it migrates, it crosses different evaporation fronts in the protoplanetary disk. And this has important consequences for the formation of these planets. Because if the planet, for example, sits exterior to the water ice line, it cannot accrete water vapor because the water is stored in the icy pebbles, and these are blocked exterior to the planet. So it cannot accrete water vapor if it sits exterior to the water ice line. Only if it moves interior to the water ice line can it accrete the water vapor. This is, of course, not only true for water, but for all the different chemical species. Then we have another constraint of these planets beside the atmospheric abundances, and this is the mass of the planets. So this is indicated by these golden and blue circles. So what we do here, once we actually reach the mass of these planets, we actually look at the composition of the planets, making the assumption that the accretion then at this point would stop. And now we can actually compare to the observations. So for this, we did not only run these 9 simulations that you see here, but we actually tested many different simulations to see if we can constrain the formation location of these planets. So the main result of this work is basically in this plot. So again, the squares correspond to the observations and the dots would correspond to our simulations. So again, this is the atmospheric abundances. And you see that actually for these planets, for WSP77AB and for the also tau Bertus B, we can actually match the observations of these atmospheric abundances. So the model in itself allows the formation of planets with supersolar and subsolar enrichment. I would like to point out here that this stellar enrichment normally happens when the planet goes into the inner disk, where all the volatiles have evaporated. And if you want to make a planet that is subsolar in the composition, you actually stay in the outer regions of the disk, where a lot of the volatiles are still in iceous form, so you cannot accrete them with the gas phase. We can, from this, of course, also conclude where these planets should have formed. So in this case, WSP77AB should form beyond the CO2 evaporation front, and tau Bertus B should have formed beyond the water evaporation front. And this gives us some constraint of where these planetary embryos should have formed. Now, you can, of course, imagine this is only 2 planets, but with James Webb, we will, of course, characterize many, many more of these planets. So we can continue playing these games and maybe get out of this an idea where these planetary embryos of the giants actually originated from. Now, there's one more thing that I would like to point out, and that is the individuality of stars. And they play a very, very important role for planet formation, especially for the composition of planets. So what you see here in this plot is the C/O ratio of stellar atmosphere, so of stars, against their metallicity, where so 0 corresponds to the solar composition, and this is basically is like a log scale. And this black line would correspond to the mean C/O ratios of the stars as a function of metallicity. But you already see that there's a huge variation in these for these stars. And this is and basically the stellar composition is what we use as an initial composition to make for our planet formation simulations. So we determine the stellar abundances. We use this for our chemical model in our planet formation simulations, and then we let the planet formation simulation take place. And this is very important, as you can see here. So what we did here in this test, we basically did our same planet formation simulation. We have a planetary embryo, in this case starting at 3.5 IU, and we try to make a tau Bertus B. But the composition of the disk basically corresponds to these different regions, where we have C/O ratios of either 0.87 or 0.35. And the planets, the composition of the planets that we get out of this is very, very different. While here, we seem to like, yeah, okay, we can kind of match the planet. But for C/O ratio of 0.35, we clearly fail to get, for example, here the carbon and oxygen abundance of this planet. And this really, really shows us that we need to have the stellar composition if we actually want to try to play this game, to link the composition of the planet with the stellar, with their formation location. So without the stellar abundance, it's basically impossible to constrain the planet formation pathway. Of course, I should mention here that, of course, there's a lot of other assumptions that go into this. For example, what we, in the measurement of the atmospheres, we just measure the atmospheres with the observations. And the atmospheric composition does not necessarily correspond to the bulk composition. So how the planet looks in its inside is, of course, still an open question that we have to understand. Here, in this case, we made the assumption that basically the atmosphere is well mixed. And basically the atmospheric composition would correspond to the bulk composition, which seems to be okay for hot Jupiters. So to summarize, everything in the disk moves. So gas, dust, pebbles, planets, nothing stands still. And the disk is the dynamic systems. To form giant planets, it seems to be beneficial to have high disk masses, early starting times, and of course also large dust to gas ratios. The inward drifting pebbles, they can evaporate and enrich the disk with volatiles. This pebble drift and evaporation can actually explain these carbon-rich disks around M dwarfs. And we can constrain the planet formation via the atmospheric abundances. But it also, to really stress this, the C/O ratio alone does not really constrain the formation pathway. And this is also what you see here. That actually, I mean, these two planets here, right? They have a very, very similar C/O ratio. Nevertheless, they formed in different regions of the protoplanetary disk. And of course, each star is individual, and we actually have to do the hard work to determine the stellar abundances in detail of these stars if you actually want to understand the planet formation and the composition of planets around other stars. With this, I thank you for your attention. I'm happy for any.
Thank you very much, Bertram. I think we probably have some questions. I see one from Keith.
Hi, Bert. I was wondering about the following thing. If you look at the observations of some of these disks with ALMA, you see that there are a lot of dust traps in the outer regions. Let's suppose that they're not because of planets, but because of something else. Then I would expect that in those disks, the pebble accretion scenario in the classical form, which you contributed to yourself, namely that the pebbles start in the outer region and then drift all the way in, that doesn't work because they are trapped in the outer disk. So would you agree? And if so, do you then expect that in the disks that have very large dust disks, that there in the inner regions there are no giant planets?
Right. Okay. Of course, if you have pressure traps in the outer regions of the disk, you will stop the flow of pebbles into the inner regions of the disk. But the question is like, do these pressure traps already exist from the very beginning? Because the disks that you observe with ALMA, they're already, like, at least to my knowledge, at least 1 to 2 million years old. And if you already reached that age, then planet formation or building the core of the giant planet is already done in the inner regions of the disk.
But if there were these dust traps, if they weren't there from the very beginning, then all the dust would have been lost and we wouldn't see it right now. Right. So the fact that we see after a few million years, we see in the outer regions of the disk huge amounts of dust. I mean, it's not 5 Earth masses, but these can be 100 Earth masses, would suggest that dust traps must have been there from the very beginning, or at least very early on, so that not all the dust has drifted inwards, isn't it?
No, of course. I mean, if all the dust drifted inwards, you cannot explain the observations. It's just the question of, like, how. Basically, I think it's a question of timing in a little bit. When did the bumps appear and what that would then imply for giant planet formation? But I mean, in principle, we have the tools. We could just run the simulation and see what happens. We just take a disk, we put some pressure bumps in there and see what happens. We could just do it. Yeah.
Question from Thomas.
So, but nice talk. You mainly talked about giant planets, but I think we want to understand planetary systems and rocky planets as well. So if I take your picture seriously, that the giant planets form very early and then they block the pebble flow, then in systems where we see giant planets, we should actually not have rocky planets in the interior. Or what is your proposal then? Because they would take normally a bit longer to grow. So would they grow even faster?
Right.
So in other words, what is your prediction if I see a giant planet or 2 giant planets which created actually a big gap? Would you expect to see a rocky planet in the interior or not?
Yes. So you actually see this here in the simulations. Okay. I mean, this is single body simulations, but I mean, as I said, the dots correspond to the timestamps, right? So, and you see here, for example, if the green simulation, you see this guy already reached this like a terrestrial mass about after 500,000 years, but the giant growing here at 3 AU needs more than 500,000 years to reach pebble isolation mass. So you can easily, so the inner planets would actually, if the embryos appear at the same time, they grow faster than the outer embryos. This is actually also what we see in the N-body simulations that we have done. So we start with a distribution of embryos, and the inner guys are the ones that grow first and reach pebble isolation mass first before the outer giants can grow. So if you have giants, you can certainly have inner planets. Well, that would depend where the embryos appear initially in the protoplanetary disk, but that's, of course, it's a different question. But in the moment you have a continuous embryo distribution, you would always have inner planets and outer planets, unless, of course, the outer planets kick everything around and destroy the inner system. But they would all grow. At least that's what you've seen in our N-body simulation.
Yeah, I have plenty of questions, so we can go on for a while. I was wondering one thing, maybe it's just because I'm a bit naive, but it seems to me that in your models, migration is no longer a problem. Seems to be that migration is solved. And in the past, I always thought that that anything that grows beyond an Earth mass would just immediately drift inward by migration and get lost. But it doesn't seem to be a problem in your case.
Yes, so I mean, we see large-scale migration in disks that have a large viscosity, so alpha 10 to the -3 and above. You have very large-scale migration. We've also seen this in the simulation that I have done, but most of these simulations, they have alpha 10 to the -4, so lower viscosity, and this actually reduces your inward migration to some level. So what happens is actually the first thing is, if you have a low viscosity and you start to grow a gas giant, you transition into type 2 migration earlier because you open the gap earlier, and additionally you migrate slower because the type 2 migration rate to some level follows the viscous evolution rate, and that of course is slower at lower viscosity. Additionally to that, I didn't say this, the simulations that we have here also include the heating torque. So basically, as you build up the planetary core, as you accrete material, you heat the disk, you get some density asymmetries, and that can actually drive outward migration. You saw this maybe in some of the cross tracks, the low viscosity, they migrate a little bit out, and this is because of the heating torque, and that also can slow down the inward migration. So the large-scale inward migration that you also see here, actually in this small cartoon here, you see this guy actually migrates quite a lot. This is because these simulations have a large viscosity, and at lower viscosity you can, to some level, evade the problem.
Okay, well, this is a very, very complex problem, clearly. I just have one question myself, very naive. You talk about embryos. I mean, the production of embryos, these are these initial masses which have enough critical mass to start growing. First of all, via the pebbles, and then later by the gas. But actually, can you predict the epoch at which that happens? I could imagine that this will depend on factors such as the thickness of the disk, and that must be very difficult to predict, because this is a problem which needs complete capture, all the heating and cooling processes and all the interactions between the particles of different sizes. Can you comment on this?
Yes. So this, I think, is one of the big questions that we have to understand. Where do these embryos form, and when do they form? So there's the different approaches. So one approach that I showed here is a little bit, we know the giants that we have, and then we can maybe trace back where they formed from. So we can, to some level, pinpoint where the planetary embryo formed, and the when is then to some level also determined within these sets of simulations, because as I showed you, if the embryo formed too late, then of course all the pebbles are gone and you would not make the giant anymore. So you probably would have to make them early on. There's of course the other approach, so basically more like the bottom-up approach, where you start from simulations. You have like your pebble distribution in the disk. You include recipes where you make planetesimals and then also planetary embryos. So Hubert Glass group at the MPIA was doing some of these simulations, and then you can determine where you could where and when the first embryos would appear. But of course, all these simulations, they're done in smooth disks. So basically what Keith was suggesting, if you have some pressure bumps, then things might actually be very different. And there's some studies that actually say in these pressure bumps, planetesimal formation should actually be enhanced. And then probably also you can make the embryos in these pressure dumps rather quickly. So it's, to some level, it's still an open question, but we are working on it.
Okay, so it sounds like you need both the observations and the theory to develop in tandem to try and pin that stuff down. It must be very complex. Well, I don't see any other questions either online or in the auditorium. So before we thank Bertram, I'd just like to make an announcement about next week's colloquium. But in the meantime, thank you very much for this very informative and interesting talk. Thank you very much.
Yeah, thank you.